Hi, thanks for coming to my talk on the extensions of the dynamic programming framework. So recently it's been reported in the news that Lake Mead, the largest reservoir in the US, is at record low levels. As you can see from this image on the left, the water line has substantially lowered over the years. Lake Mead is the reservoir that is connected to the Hoover Dam, and this has resulted in the electrical generation of the Hoover Dam decreasing over the years from the year 2000 to the year 2020. So the Hoover Dam is a hydropower turbine. These turbines just make up 11% of the electrical power generated by America, but they have a special property that they're able to turn on in just 0 to 10 minutes. Traditional steam power turbines, they make up a larger percentage of the energy generated in America, but they take longer to turn on, 1 to 12 hours. And nuclear plants take even longer to turn on. So why is it important to have generators that can come online quickly? Well, the answer is to prevent power cuts due to increased electrical demand. So as a case study in Phoenix, the temperature regularly exceeds 40 degrees Celsius. There's over 4 million people in the Phoenix metro area. It's the second fastest growing city in America. Over 20% of the residents are elderly. Heat waves that often occur in Phoenix in the summer put tremendous strain on the power grid because many of the residents turn on the air conditioning units and other appliances. Combined with the fact that the Hoover Dam now has reduced electrical output that helps to support Phoenix, we may get more power cuts in the future, which are dangerous because many of the air conditioning units will turn off. So to curtail power surges, electrical companies have now changed the way they bill customers. So traditionally, the electrical bill of customers was just based on the time of use charge, and this is represented in green. If we denote the power required by the customer at some time k by Q grid, then the time of use charge comprises is proportional to the amount of power required by the customer during off-peak and on-peak times. And now electrical companies have introduced a new type of charge called a demand charge, and this is based on the maximum amount of electricity the customer requires from the grid during the billing period. So if we consider the power used by two customers over time, a red and a blue customer, the area under the graphs of the two customers are roughly equal. So they require roughly the same amount of electricity. So the time of use charge will be fairly similar. But the red customer has a higher peak demand for power. So because of the demand charge, we would expect the red customer to have a higher electricity bill. So what can consumers do to reduce their bills? They could install some sort of energy storage in their house, like a residential battery. And then they could charge and discharge the battery in a way to reduce their maximum power consumption. So this naturally forms an optimization problem, where the decision variable is how you charge and discharge the battery. And the objective function is just the time of use charge plus the demand charge, which is the electricity bill for the customer. And the constraints are the battery constraints. So if Q battery is greater than 0, that means the battery is charging, and if it's less than 0, that means the battery is discharging. Now, this optimization problem is very hard because the objective function is non-additively separable. So the demand charge term with the maximum, where the cost now depends on the entire state history, means that this problem is challenging to solve by more classical methods, which we'll discuss next. So now we'll discuss classical dynamic programming theory. So what is dynamic programming? Dynamic programming is a class of methods used to solve optimization problems. All of these methods share these three properties. The first property is that they break the optimization problem up into a simpler class of subproblems. They store information about the solution to each of these subproblems, and they use the stored information to help solve the global problem. So a type of problem dynamic programming is used to solve is represented in this graph, where the node on the left is the starting position and the node on the right is the finish position. And the algorithm is solved by finding the path with least cost from the start to the finish. And when you transition between two nodes, there's a cost of that's depicted on by these numbers. So a greedy algorithm might choose to go upwards first because it only occurs a cost of -2 compared to 1. However, later you would end up occurring a cost of 3 or 5. So the optimal strategy is to go where the bold line is. And this is the type of problems that dynamic programming can solve. So the type of optimization problems that are usually considered for dynamic programming purposes are called multi-stage optimization problems. They're multi-staged because they occur over a certain period of time. And they're solved by finding a sequence of inputs that minimizes a cost. So in this diagram, we've represented a multi-stage optimization problem where there's an agent represented as a dog. And the agent is initially at some state, xt, and the agent can choose an action, ut, that interacts with the environment. And the environment then updates the state and provides a cost based on the previous state and input. So these multi-stage optimization problems come in several flavors: model-based or model-free, finite time or infinite time, deterministic or stochastic. In this talk, we'll mostly be talking about model-based, finite time, and deterministic problems. And in the second half of the talk, we will also be considering the analogous continuous time formulation of the problem. So to mathematically describe multi-stage optimization problems, we'll first consider a one-stage example. Suppose the agent is a dog, and we can represent the dynamics of the dog using this very simple equation that has a state and an input. Then if the dog is initially at a state that we label as 0, if the dog chooses to use an input of +1, then according to the state dynamics, the dog will move to a state +1 that's represented as the dog kneeling, and will receive a reward of 2 sweets. If the dog chooses to use an input of 0, then the dog remains at state 0 and receives a 1 sweet reward. If the dog chooses to use an input of -1, then according to the state dynamics, the dog moves to a state -1, which is the dog misbehaving, and receives no sweets. So equivalently, you can formulate this in terms of costs, where instead of trying to maximize the reward, you're minimizing a cost, and you just change the sign of the rewards. So this was over one stage, and the solution is trivial. The agent should pick an input of +1 to receive the maximum reward of 2 sweets. So over multiple stages, this forms an optimization problem of this form. where the decision variable is u star, and u star is an input sequence from the time 0 to the terminal time. And the goal of the problem is to minimize the additive costs, and that's subject to the state dynamics and the state constraints and the input constraints. So a quick definition here is that the objective function that is of this form is called additively separable. So how do we use dynamic programming algorithms to solve optimization problems of this form? Well, rather than trying to solve the global optimization problem, where we have to choose an input sequence from the initial beginning of the optimization problem to the terminal time, we could instead solve the tail problem from t equals -1 to t. And then we could solve the tail problem of t-2 to t-1, and then use the solution of the previous tail problem to help solve this. So intuitively, if you were to write this down mathematically, you would get a recursion equation called BELLMAN'S equation that's given in this box here, where V represents the optimal cost to go from starting from a state x and time t. If you can solve BELLMAN'S equation, then you can synthesize an optimal input sequence according to these equations here. And we can see that it's simpler to solve BELLMAN'S equation because you're only minimizing over one input at a time, rather than minimizing over math bold U, which denotes all of the inputs. And solving BELLMAN'S equation is a dynamic programming algorithm because the value function stores the solution to each of the tail problems. And the value function is this function V that satisfies BELLMAN'S equation. So next we'll move on to the ways we've extended the dynamic programming framework. So the first part of the talk is based on our proposed state augmentation methods, and that was presented in papers in TAC and CDC. So if we recall, the consumer electricity costs can be written in this form. The time of use costs take this additively separable structure that looks like this. And if it wasn't for the demand charges, then we could solve the problem using classical dynamic programming. But the fact that we have demand charges means that we need to extend the theory in some way. Because now, if an agent makes an input, a decision of the input, then the cost now doesn't just depend on the previous state and the previous input chosen. This cost is a maximum term that depends on the whole history of the state sequence. So we'll next generalize the type of cost functions that we consider in our multi-stage optimization problems. And this class of functions will include costs that occur in the battery scheduling problem. So this class is called forward separable functions, and they're functions J that can be written in this form of a composition of these psi maps. And these psi maps, in a way, the composition starts at 0 and goes forward in time to the terminal time of the problem. So if we consider a multi-stage optimization problem where the objective function is a forward separable function, and well, we have the usual state dynamic constraints and state constraints and input constraints, then we can do this augmentation trick where now we extend the state space to be a variable Z1 and Z2. So Z1 corresponds to the original state dynamics, the base xt plus 1 equals fxt. But Z2, the extended dynamics, depends on the objective function that involves these psi's, and also the objective function changes in the augmented problem. And now this only depends on the state space at the terminal time. So we can show that these two problems are equivalent. The augmented problem can be solved using classical dynamic programming theory by just solving BELLMAN'S equation. The problem is the augmented problem now has a higher dimensional state space, which means it's computationally more challenging to solve BELLMAN'S equation. And we also showed that we can actually do this augmentation trick for any objective function, but this involves naively choosing the psi maps in a way that the state space would grow with respect to time, which is bad. So intuitively, these psi maps carry the information necessary for a decision maker or agent to act optimally. And this information we include in the state space to propagate through, because the agent has access to the previous state of the system. So we use this state augmentation method to solve the battery scheduling problem. And if you see, the red represents the on-peak time, and the first graph represents the power required by the customer from the grid, and the last graph represents the battery energy level that the customer has in their house. So as you see, as we approach the on-peak, the battery begins to charge, and during the on-peak period, the battery discharges. And this results in the power being stabilized, and there's not many peaks. So this would reduce the demand charge. So this type of methodology has the potential to save customers money, and also reduce the need for grid reserves, because there'll be less peak demands. And this can help keep Lake Mead reserves high. So next we'll move on to another way we've extended the dynamic programming framework by generalizing BELLMAN'S equation. And this was presented in Automatica. So if we consider Dubin-Carr's dynamics, so this is dynamics of the form xt plus 1 equals fxt ut, as we have been considering dynamics of this form. It has some nonlinear trigonometric terms, and also the input is in the third dynamic equation. And this models a car which has fixed velocity v and a fixed turning radius, and the input allows us to point which direction the car is facing. So an elementary problem would be to find the input sequence that drives the state to some goal set S. So this would be the same as minimizing an objective function, which is the first time the state enters the state S, with some cutoff of the terminal time. So this objective function does not seem to be of this additively separable structure. For general dynamics, it doesn't seem to be of this additively separable structure that we can use classical dynamic programming for. So we could use the state augmentation methods that we developed previously in the previous part of the talk, but this would result in increasing the state space and making the problem more complicated. So in this part of the talk, we'll look at methods that don't involve state augmentation. So for this, we consider a new type of objective function. These are not forward separable, these are backward separable, because they're written in a form, again, as a composition of maps. But these maps, the composition starts at the terminal time and then goes backwards in time. So we call them backward separable. And they also have a monotonic property, which these maps must all be monotonic in their third argument. So examples of functions that are monotonically backward separable, you can show that the classical additively separable functions are. which implies this generalizes the classical dynamic programming theory if you can solve multi-stage optimization problems with this type of objective function. Also, point-wise maximum costs. But if you were to add a summation of costs with this objective, then that turns out not to be monotonically backward separable. So for those type of objective functions, you would have to use state augmentation. And unfortunately, that's the same class of problems that the battery scheduling problem was. And also the minimum time of the state to get to some set. This type of objective function turns out to be monotonically backward separable. And we can prove all of these are monotonically backward separable by finding these specific phi maps and show that the phi maps are also monotonic in their third argument. So we would like to solve problems with an objective function of this type of cost without using state augmentation. So if we consider a multi-stage optimization problem that has this type of objective function that's monotonically backward separable, and it has the usual dynamical equation and state constraints and input constraints, then clearly, because of the composition, this is of the classical case where you make an input and you get a cost based on the previous input and state. So we were able to generalize Bellman equation to solve problems of this class. Now the Bellman equation involves these phi maps. And we showed that if you could solve this equation, then you can derive an optimal input and optimal state sequence according to these equations. And solving this generalization of Bellman's equation requires no state augmentation. So we solved our generalization of Bellman's equation to minimize this objective function for the Dubin's car dynamics. The graph on the left shows a blue square, and that's the goal set S. And it shows obstacles that we also were trying to avoid. And it shows 3 initial starting conditions, and the controller successfully points the car in the correct direction, such that the car gets to the blue square as fast as possible. And we also did the same thing for different dynamics. Now there's 3 inputs, and this is in 3 dimensions. And the graph on the right shows various initial conditions and the control and the input sequence driving the dynamics to the goal set, which is this this square blue region. So next we'll move on to algorithm we proposed based on sum of squares programming to solve the Hamilton-Jacobi-Bellman partial differential equation. And this is based on work that we've submitted to TAC and CDC. So if we consider the discrete time multi-stage optimization problems, in the classical case, they have this type of objective function that's the sum of costs, and they have this state dynamics. We can recall from earlier in the talk that if we can solve the Bellman equation that's given in this green box, then we can solve the discrete time problem. In the continuous time case, now the cost is an integral rather than a summation. And the dynamics are an ordinary differential equation rather than a recursion equation. And analogous to the discrete time case, if you can solve this optimality equation called the Hamilton-Jacobi-Bellman partial differential equation, or HJB-PDE for short, then you can also solve the continuous time problem. So here's some facts about the HJB-PDE. It's a nonlinear PDE due to the infimum. So the function you're trying to solve for is this V function that's blue. And it seems to enter linearly. but there's an infimum that makes this nonlinear. And nonlinear PDEs are very hard to solve. It can be shown that there's a unique solution to this PDE, but this is a viscosity solution. So this is a generalization of the classical solution. And this means that this solution might not be differentiable. Solutions to the HJB PDE we call value functions. And value functions intuitively are the optimal cost to go of the tail problem. So if V star satisfies the HJB PDE, it also follows they must equal the minimum or the infimum of the input integrated from time t, where t is the argument, to the terminal time initialized at x of the cost. So we know that value functions exist, but we don't have a general analytical formula for them. This is not an analytical formula because it has an infimum. It's actually an optimization problem, and it's optimizing over inputs, which are functions in time. So it's also an infinite dimensional optimization problem, and it's very hard to solve for. Yeah, and if you can, value functions give the optimal cost to go. So they're solutions to the tail problem. And there's some notation here. Rho f means the solution to ODE. So the underlying state dynamics are x dot equals fxu. And we say rho f, where the f corresponds to the vector field, is the solution map if it firstly satisfies the ODE and at time 0 equals the initial condition. And like value functions, we know the solution maps exist, but again, we don't have any analytical formulas for them. So if you can solve the HJB PDE, then you can substitute the solution into this equation, and you can get the optimal controller. So the HJB PDE is played historical importance to control theory, and has derived the famous Riccati equation for LQR control in the special case where the cost is quadratic and the dynamics are linear. Solutions called value functions to the HJB PDE can also yield reachable sets of nonlinear ODEs, which we'll discuss further in the talk. And since this is a very challenging PDE to solve, it's usually solved through discretization. But in this talk, we'll present a new method that doesn't involve discretization. So if V star is some value function, we're interested in approximating it. We're interested in approximations that are uniformly less than or equal to the value function. First, we note that it can be shown if V satisfies this linear dissipation inequality, these two linear dissipation inequalities, then it can be shown that V must be uniformly less than or equal to the value function corresponding to the problem with vector field F. So let's return to the problem of trying to find the value function. We want to find V that satisfies the HJB PDE. The problem is this is a hard PDE to solve, so we relax the problem. To relax the problem, instead of solving for equality signs, we solve for inequality signs. We also remove the infimum to make the problem linear and enforce the inequality constraints over all of U. Because this is a relaxation, so any solution to the HJB PDE also satisfies these constraints. But also many other type of functions satisfy these constraints. So since we're interested in our approximation, we add an objective function of the L1 difference between our decision variable and the true value function, where we recall the true value function is given by the optimal cost to go of the tail problem. So we don't actually know what the true value function is. We're trying to approximate it. So as things stands, we can't approximate this problem because V star is unknown. However, from the previous slide, we'll recall that if V satisfies these constraints, so it's feasible to the above optimization problem, then it's less than or equal to the true value function. If we use this fact, and we can use this to reformulate the objective function by removing these absolute inequality signs. And now the objective function has two components. The first component is just a constant because it just involves the value function. So we can actually remove this from the objective function. And rather than minimizing over the negative of the integral of V, we equivalently maximize over the integral of V. Now we have an optimization problem that's linear in the objective of our decision variable, which is a function. So once we get to this optimization problem, we'll assume that the solution is polynomial, which we denote as mathcal D. And once you get to this stage where you have a polynomial decision variable, an objective function and constraints that are all linear in the decision variable, you can use a technique called SOS programming to solve the problem. And well, you also further need that the vector field F is polynomial. And SOS programming is a procedure where you tighten the optimization problem, and instead of enforcing the inequality constraints, you now force the constraints to be SOS constraints, where sum of squares polynomial is any polynomial P that can be written as the sum of squared polynomials. And this, of course, assumes that the input and state constraints take this semi-algebraic set form. Then you can solve this sum of squares optimization problem on the computer using software like SOS Tools and Sadumi and MATLAB. So given our sum of squares programming problem, we showed that if V star is a solution to the corresponding HJB PDE, then under mild conditions, you can show it's also Lipschitz continuous. And you can use this fact together with mollification to show that as we increase the degree of our SOS optimization problem, so we're searching for functions of higher and higher degree, that these functions converge to the true value function in the L1 norm. So next we'll talk about how we can use this SOS algorithm to actually synthesize optimal controllers. If we consider optimal control problem that's affine in the input variable, so that means the input variable appears linearly in the costs and in the dynamics. And also we would like to have a constraint where the input is between is constrained to be in a rectangular box -1 to 1. And if we recall that if you can solve the corresponding HJB PDE and get some V, then you can substitute V into this equation and get our optimal controller. So if we put in our affine cost functions and affine dynamics into this equation, we see that the U's appear linearly. And we're optimizing over -1 to 1. Now, if you're optimizing a linear function from -1 to 1, then clearly the minimum will occur at the extreme points and never in the middle. So this intuition leads us to eliminate the infimum of this equation and get an analytical formula of this form. So if we could solve the HJB PDE and substitute V in, we can derive an optimal controller. Now, it's hard to solve the HJB PDE, but we can approximately solve it using our SOS algorithm that we discussed previously. So we will substitute our approximate value function into this equation to derive controllers. So here's a numerical example where thus, for starters, is affine in the dynamics and the cost in the input variable. See, the input variable only occurs once and is linearly inputted into the dynamics. The cost is to minimize the state, the distance between the state and some scalar q and some coordinate q. Q is in the R2 because the state space is in R2. According to the equation on the previous slide, the optimal controller takes this form. But instead of substituting V as the true value function, we substitute a degree 14 value function derived from our SOS optimization problem. And then we see how well this function minimizes the cost of this problem and the state dynamics. So in this graph, you can see that the green trajectory corresponds to just using an input of 0. And the trajectory is initialized up here, and it goes around to create the classical van der Pol oscillator. The red trajectory corresponds to the derived controller from our SOS programming problem when Q is the origin. So we can see the controller successfully drives the state towards the origin and circles the origin and terminates nearly exactly at 0, and that's given by the black dot where the trajectory terminates after the terminal time, which is 5. And there's also a terminal cost, so you can see the trajectory is trying, the controller is trying to get the state to finish as close to Q as possible. And a similar thing is happening with the blue trajectory when Q is minus 0.40. We can evaluate the costs associated with each of these trajectories and compare them to naive inputs, such as using a constant input of 0, +1, or -1. And we see that the SOS derived controller performs better than those other types of controllers. Next, we'll briefly talk about how this same SOS algorithm can be used to provide approximations of reachable sets. So recall that if a function satisfies the HJB PDE, then it can be written in this form as the optimal cost to go, where the rho function corresponds to the solution map of the underlying time variant process. If the cost function C is 0, then this equation simplifies. So we just get a terminal cost. Now, if we consider if x is used in as the argument of the value function at time equals 0 and that's less than 0, according to this equation here, that implies that there must exist a controller such that the solution map enters the 0 sublevel set of G. So this implies that the sublevel set of V less than 0 is the set of initial conditions that can reach the sublevel set of G. And this is equal to the backward reachable set of the problem. And by reversing time, which is simply just changing the sign of the vector field, we can also calculate the forward reachable set, which we do numerically in this problem. We consider the Lorenz attractor, which is a 3-dimensional system that's actually well studied because of chaos theory. And this green ball that is basically the set, the sublevel set X, that Gx is less than 0 for some G that we've chosen for our algorithm. And each of the green dots correspond to an initial condition that we've used the ODE solver to simulate forward in time. And for 3 of them, we've plotted their trajectories as well, and they terminate at the red points. So the forward reachable set must contain all of these red points. Using our SOS algorithm, we look at the sub-level sets of our derived value function, and this is given by the cyan region that clearly contains the reachable set, as we expected. Next, we'll move on to the final way we extended the dynamic programming framework, and this is on the topic of converse Lyapunov theory, and recently it was accepted for CDC this coming in December. So if we consider a 9-state mathematical model that represents the F-18 fighter jet, this model is written as an ordinary differential equation, as we've considered before. And the state space corresponds to various parameters such of the airplane, like the velocity and the angle of attack. There's also an input, and we can control several things on the airplane. But for the purposes of this talk, we'll assume that the input is given, and therefore U is absorbed into F. So we just consider systems x dot equals Fx. So the F-18 fighter jet is infamously susceptible to a mode called fallen leaf mode. So when the state space enters a certain region, so when X is in some region, we see that the airplane starts to exhibit unstable oscillations where there's large fluctuations, for instance, in the angle of attack and the slight side slip. So for instance, well, this is clearly very unsafe, because if you imagine an airplane and the angle of attack is the angle in which the airplane is pointing, if this varies too much, then the airplane is well, in an unsafe mode. And a paper from 2011 has simulated this ordinary differential equation and found the fallen leaf mode through simulations, and we can see the unstable oscillations in the state space. And this alpha corresponds to the angle of attack, and we see that the angle of attack can vary from nearly 80 degrees to minus 20 degrees. So all of this is very unsafe. And the goal of our research is to develop methods to search for regions where the system does not exhibit this type of unsafe behavior. The system exhibits more steady state behavior, and we call this stable. So if we consider some general ODE, we'll assume that it has an equilibrium point at 0. We can do this without loss of generality, because if it has an equilibrium point at any other point, say x0 and Rn, then you can make a linear transformation to make the equilibrium point at 0. We'll define the solution map again, but there's no input this time. The solution map is still denoted as rho f. It satisfies the ODE, and also at time 0 equals the initial condition. We'll also call the trajectory the solution map fixed from a fixed initial condition propagated forward in time. So next we'll define what stability is mathematically. We say a set U is asymptotically stable if it contains a neighborhood of the origin, and for any initial condition in U, that the solution map stays in U, and also the solution map converges to the origin. Furthermore, if this rate of convergence to the origin is bounded by an exponential function, we call this exponentially stable. So the region of attraction, which is the region of, you can intuitively think of it as a region of stability, is the set of all initial conditions such that the solution map converges to the origin. And you can think of this as the union of all asymptotically stable sets. And we denote it as ROAF, where the subscript F corresponds to the vector field of the ODE in question. So we'll briefly go through some properties of solution maps. So unlike linear ODEs, there's no analytical solution, because in linear ODEs, we have x dot equals AX, and in this case, rho fx t equals e to the power, the exponential matrix times x. But in the case of nonlinear dynamics, where f can take any form, fx isn't necessarily ax, there's no analytical equation for the solution map. But we do know the solution map exists by a technique called Picard iteration. And also, from this technique, we can prove several smoothness properties of solution maps. And it turns out that a solution map is as smooth as the vector field f is associated with, as a rule of thumb. Also, for any initial condition, we can approximately simulate the trajectory using MATLAB or any other ODE solver. So let's recall the definition of the region of attraction of all initial points that converge to the origin. The problem that we're trying to solve is we need to find a set S that's contained inside of the region of attraction and also approximately equals the region of attraction. One way you could potentially go about solving this problem is to just pick a S, and then for each initial condition inside of that S, simulate the trajectory for some sufficiently large time period and show that it's arbitrarily close to the origin. But the problem with this is that there could be uncountably many points in the set S. So you can't simulate uncountably many things. And also there's an error in the simulation. So rather than relying on Monte Carlo simulations, we search for Lyapunov functions. So given an ODE defined by some vector field f, a Lyapunov function v is a function that has a domain omega and maps to the reals such that it's positive and 0 at 0, and also satisfies this inequality that intuitively means it decreases along the solution map, and that is for all points in its domain except the origin. So if you can find such a Lyapunov function v, and you can also find a scalar b such that the sublevel set, the b sublevel set of v is contained in its domain, then it follows from some elementary theory that the b sublevel set of v is contained inside of the region of attraction. But the converse Lyapunov function is converse Lyapunov question is much more interesting. Given an asymptotically stable ODE, does there always exist a Lyapunov function that can certify this stability? And can we use this Lyapunov function to approximate the region of attraction arbitrarily well? So we would rather find Lyapunov functions because this doesn't require any knowledge of the solution to the ODE. You see from these properties that they satisfy, none of them involve rho f, which is the solution map, which is unknown, so that's good. So we can try and prove the existence of converse Lyapunov functions by constructing them based on the solution map rho f that we know to exist. And then we can prove that they exist, and then after we prove that they exist, we can design algorithms to search for them, and then approximate the region of attraction using them. So the most commonly used type of Lyapunov function to approximate regions of attractions is called the maximal Lyapunov function. It was first proposed in 1949 by Messera, and then in later work in 1985, the analysis of that it can approximate regions of attractions was done. And this converse Lyapunov function takes the form as an integral from time equals 0 to infinity of the solution map with a squared Euclidean norm. And it can also be shown that the infinity sublevel set of this maximal Lyapunov function exactly gives the region of attraction. So the first thing is to note that this type of converse Lyapunov function is just a special case of a value function. The value function integrates the solution map inside of a cost function a long time. In this case, the cost function Cxu is simply just the Euclidean norm squared. So we can use our intuition and our SOS algorithms that we previously talked about to try and search for or approximate such converse Lyapunov functions. But the problem is this converse Lyapunov function is unbounded outside of the region of attraction. So it takes values of infinity. And you can't use sum of squares programming to approximate unbounded functions because polynomials are continuous and unbounded functions are discontinuous. So recently in the paper that will be presented at CDC, we proposed a new type of converse Lyapunov function, and it shares some similarities to a converse Lyapunov function in Zubov 1964. And it has like this, it can be thought of as an exponential transformation of the maximal Lyapunov function, because V star seems to be inputted up here. It depends on scalars alpha and beta. And the good thing is outside of the region of attraction is 1, so it's bounded, so we have a better chance of approximating this by a polynomial. So consider ODE and our newly proposed converse Lyapunov function. We can show that the one sublevel set of this Lyapunov function is exactly the region of attraction. If you can find a ball of radius ether that's exponentially stable for our system, you can show that for sufficiently large alpha and beta, our converse Lyapunov function is globally Lipschitz continuous, which is an important property when trying to approximate it by polynomials, because this Lipschitz continuity property is the same property we use to show our convergence to the value function. And also for sufficiently large alpha and beta, you can show that V satisfies a PDE, and this PDE looks very similar to the HJB PDE. So we will be using a similar solution method to solve it. So to approximate the region of attraction, we will actually indirectly approximate it by solving the PDE to find our converse Lyapunov function, because the one sublevel set of the solution to this PDE gives the region of attraction. But it's hard to solve PDEs. So we change these equality signs to inequality signs and relax the problem, and also add an objective of the L1 norm between our converse Lyapunov function that's given as this form and our decision variable. So here's our optimization problem, and there's our converse Lyapunov function. Currently, we can't solve this problem again because the objective function involves an unknown function. But if we consider the functions that are feasible that satisfy these two inequality constraints, it can be shown that these functions must be uniformly greater or equal to the converse Lyapunov function. And we can use this to simplify the objective function and remove the converse Lyapunov function from the objective function. So here's our optimization problem again and our converse Lyapunov function. And from the previous slide, feasible V are uniformly greater or equal to the converse Lyapunov function. And if we use this fact, we can evaluate the objective function into the form of two components, and the second component is just a constant, so we can eliminate it from the objective. And we form an equivalent optimization problem that's now linear in the decision variable V and involves no unknowns. Once we get to this stage, well, firstly, we'll enforce it, these inequalities over some sufficiently large ball of radius R, and we'll also assume F is polynomial. And we do the usual SOS tightening, where this sigma to the power of D underscore SOS denotes the sum of squares variable, and mathcal D denotes polynomials. And we can just solve this on the computer using available software. So given our SOS problem and our ODE, we were able to show that for sufficiently large alpha and beta, where how large depends on the exponential stability of the problem, the local exponential stability, that the solution to the D degree SOS optimization problem, PD, the one sublevel set, converges to the region of attraction with respect to some metric called the volume metric. And also the one sublevel set is contained inside of the region of attraction. So we run our SOS algorithm to find regions of attractions of several systems, like the van der Pol oscillator given by this ODE. The red line corresponds to the true region of attraction, and the black line corresponds to the region of attraction that our algorithm yielded for degree 12. The rectangle is just the region we integrated the objective over, and the ball, the green ball, is just the region we enforced our constraints over. And you can see that our approximation of the region of attraction is very, very close. Now, for a three-dimensional system given by this ODE, we also did the same thing. We run our SOS algorithm for degree 10, and this yielded a sublevel set that's given as this gray region that represents the region of attraction. And these red points and blue points and green points are initial conditions that we simulated the ODE for, and we labeled them red if they were unstable, so they diverged and they didn't converge to the origin, and blue and green if they did converge to the origin. If our approximation contained the point, we would color it green. And as you can see, it's a fairly good approximation because there's very few points that are blue, that are inside of the region of attraction, but not given by our approximation. So in summary, in discrete time, we showed that for a class of cost functions called forward separable cost functions, you can use state augmentation to solve the associated multi-stage optimization problems. We use this method to solve the residential battery scheduling problem and successfully minimize both time of use and demand charges. For another class of cost functions that we coined monotonically backward separable cost functions, we generalized BELLMAN'S equation to solve optimization problems with this class of objective functions. For continuous time, we proposed a sequence of SOS problems, they yield polynomials that converge to solutions to the Hamilton-Jacobi-Bellman equation in the L1 norm. We use these approximate solutions to synthesize near optimal controllers and also bound reachable sets. We also proposed a new converse Lyapunov function and used the intuition that it was really a specialized version of a value function to also derive a SOS optimization problem to approximate the region of attraction. And with that, I would like to thank my advisor, collaborators, colleagues, and committee members, and also the audience. Are there any questions?